Hello, welcome back to the first course in general physics, and in this lecture we will be discussing the first part of the elements of fluid mechanics. So we will be changing the pace and topic to the study of fluids. Fluids are interesting for our study because they are all around us. They are surrounding us and they exist in almost all aspects of our life. So in this part of the lecture, we will be discussing the density and pressure, which are the elements that we would need to study the mechanics of fluids instead of mass and volume and so on. And we will discuss the problem of fluids at rest and deal with the problem of evaluating the pressures in a fluid. And after that, we will come to discuss some techniques used in measuring the pressure. We will talk about the mercury barometer, which is an instrument that used to measure the pressure of the atmosphere. And then we will talk about the open tube manometer, which is used to measure the pressure of a gas contained in a certain volume. After this, we will go on to study Pascal's principle and some of the applications as one of the applications of the principles of mechanics of fluids, and Archimedes' principle. Then we will take into consideration the motion of fluids, the dynamics of fluid. And in this case, we will only discuss the motion of an ideal fluid, because the motion of a non-ideal fluid is a particularly difficult problem to solve. So in this elementary course of physics, we will be discussing only the motion of an ideal fluid. We will obtain the equation of continuity for this fluid, and we will discuss Bernoulli's equation. At the start, we start with a definition of the fluid. What is a fluid? A fluid is a substance that can flow, and thus it includes both liquids and gases. This is what a fluid is. A fluid, as we know from our experience, conforms to the shape and the boundaries of the container in which we put it. So it takes whatever shape of a container we put it in. And that is a consequence of the fact that a fluid cannot sustain a force that is tangential to its surface. So it just takes the form of the container that it is in. However, although it does not sustain any tangential component of force, it flows if you pull on it tangentially. However, the fluid can exert a force that is in a direction perpendicular to its surface. So if we assume that we have a fluid and there is a surface in it, the fluid does exert a perpendicular force to that plane. Why study fluids and fluid motion? Fluids are very essential substances in our everyday life, and we cannot think of almost any example of our everyday life activity that does not involve fluids in it. For example, oceans and the atmosphere consist of fluid, are made up of fluids. We breathe fluids, we drink fluids. Fluids exist in our food, fluids exist in our body. The fluids are very essential in many other various aspects of life. They are essential for the motion of machines. A car will never be driven without a fluid. Any other machines also need fluid to be driven to work. Our life, our blood consists of fluid. Our body is mainly water. And the fluid, in addition to nourishing the motion and the life, also it introduces sometimes effects in changing the landscape. For example, the surface of Earth is changed by the effect of fluids, whatever it is, whether it is the rains, heavy rains, the flow of rivers, the floods, or the strong winds, which can change the shapes of the surface or the mountains or introduce new hills or whatever. It has a great effect in our life and the landscape around us. Now, in the context of the discussion of motion of objects, we were concerned with the quantities mass and force, and we related these two quantities, mass and force, to study the motion of objects. In fluids, what mass shall we talk about and what force shall we talk about? It is much more convenient to select other quantities in order to study the motion of fluids. And instead of mass, we talk about the density of a fluid, which is related to the mass. It's mass per unit volume, actually. And we select the pressure as the dynamical quantity instead of the dynamical quantity F. And pressure, indeed, is related to the force F. So instead of choosing the mass and force as quantities relevant to our study in motion of fluids, we choose the density and the pressure. And in a little while, we will know how to use the two quantities in the context of studying the motion of or the static state equivalently of the fluids. The density is defined as the mass per unit volume. So if we define the density in the most general form, at a given point in the fluid, we would pick a small element of volume delta V, we would measure the mass within that volume element, if we call it delta M, then the density of the fluid at that point around the element of volume delta V is given by the ratio of the mass contained in delta V divided by the volume delta V. So delta M divided by delta V is the density of the fluid at the point from which we picked the mass element delta M. In general, the density of a fluid, if we take this general definition, it applies to whether the density is uniform, constant across the fluid, or if it is variable. However, in the special case of a uniform fluid, in which case we have the density is constant as a function of position inside the fluid, in this case the density is simply the total mass of the fluid divided by its total volume. This, in general, if the density is not constant, this formula will give the average density. If we take the total mass divided by the total volume, in general, it gives us the average, a formula for the average density of the fluid. But if the density of the fluid is constant, then the average density is equal to the density at any point in the fluid. And in that sense, rho equals m over v is the density of a uniform fluid. The units of the density, as we can see from the formula, is units of mass divided by units of volume, which is simply, in the international system of units, is kilogram divided by meter cube. That is the density unit. Now, let's discuss the pressure, which is the other quantity that we would need for the study of the mechanics of fluids. And if we assume that there is an element of area delta A inside a fluid, consider in the sea, for example, if you imagine a small area delta A, the fluid would exert a force, if we call it delta F, on this area, on this element of area delta A, and that force is normal. And the definition of the pressure is that the pressure that the fluid exerts on the element of area on one side of that area is equal to the magnitude of the force delta F divided by that area, delta A. So delta F by delta A is equal to the pressure. And if we pick the area at a given location in the fluid and see what amount of force does the fluid exert on that area, then that will give us the pressure at that point in the fluid. And in general, the pressure varies with position. If the pressure in a fluid is uniform, then if we have a flat area A, not necessarily a small element, because the pressure is uniform, if we take the whole flat area and measure the total force acting on that area, exerted on that area, and the total force divided by the total area is equal to the pressure. exerted on that area. Again, this formula in general gives the average value of pressure. In case if the pressure is varying from one point to another, then the total force divided by the total area is a measure of the average value of the pressure. But if the pressure is uniform, then the average value is equal to the value at any point, and thus this will give us the pressure at any point in the fluid if the pressure is uniform. The pressure is a scalar quantity. It's not like the force. And the units of pressure, as the definition implies, is in the international system Newton per meter square. It is the units of force divided by area. That is Newton per meter square. And that unit is called Pascal and abbreviated as capital P small a. So the Pascal will be the unit of pressure in the international system of units. There are other units that people use in everyday life for measuring the pressure, and one of them is the atmosphere, ATM, where we can, for example, say that the pressure inside a tire of a car is 30 or 35 atmosphere. What is the atmosphere? It is the atmospheric pressure at sea level almost, and this is equal in terms of the international system of units. It's equal to 1.01 times 10 to the 5 pascals. That is 101,000 pascals. That is the value of the atmospheric pressure, the unit ATM, which is the atmospheric pressure at sea level. And another unit for measuring the pressure is the so-called torr, where the relation between this unit and the other units is that one atmospheric pressure, which is 1.01 times 10 to the 5 pascals, is equal to 760 torr. And yet another unit is in terms of the British units, and that is given by pounds per inch square. Pound is the unit of force, which is the weight, since in the British system the weight is the basic is one of the basic quantities, not the mass. So pound is a unit of force, and inch square is the unit of area in that system, and thus we get this unit in the British system, and it is related to the previous units by the fact that one atmospheric pressure, 1 ATM, is equal to 14.7 pound per inch square. So this formula gives us a relation between the different types of the pressure, the different types of the units of pressure. The ATM unit, as we said, is the approximate atmospheric pressure at sea level. That's the convention for it. When we say 1 ATM, that's the atmospheric pressure at sea level. And the torr is a millimeter of mercury, millimeter Hg, as measured in the mercury barometer, to be discussed a little bit later. And now we are at a point where we can start discussing the mechanics of fluids after we have defined the relevant quantities, and we will be discussing fluids at rest in the beginning. Fluids at rest. Let's consider a container containing fluid. as shown in this figure. This figure shows the surface of the fluid, which is set as y equal to 0. So the origin of the coordinates, which is necessary for the study of the mechanics of a system, is set at the surface of the fluid in the container. And we consider the y-axis as the axis upward. So upward over the surface of the fluid is the direction of increase of this coordinate y, with y equals to 0 at the interface between air and the fluid. And let's consider a sample of the fluid beneath the surface, inside the fluid beneath the surface. And for that sample, let's pick up a right cylindrical sample of base area A. So the top area of the cylinder and the bottom area is A, and the height of the cylinder is extending from the position of the upper base, which is at y1, which is the upper level of the sample, and the lower base or the lower level of the sample at y2. Remember that y1 and y2 are the depths of the upper and lower bases of the right cylinder, and both of them are negative numbers because the y coordinate of each one of them comes below the 0 reference point. So we assume that level 1 at depth y1 beneath the surface is at pressure P1, and we call the pressure at level 2 as P2, and we are ready to analyze the equilibrium situation of this mass sample. Notice that this sample under consideration is in equilibrium. It doesn't move. If you have a spot or an element of the fluid inside the ocean, for example, if we don't have drifts or general motion of the fluid, if the fluid is static, then that element of the fluid is also static. It stays there forever. Thus, we conclude that the total forces acting on this sample of fluid is 0, according to Newton's second law. So the free body diagram of the sample is this to the right of the figure in B, where we see that the fluid influences the sample by pushing on the lower base at y2, pushing it upward by a force F2, and there is another force which is pushing on the upper level of the cylinder, upper base of the cylinder, where the fluid pushes it down. That is F1 pointing downward, and there is the weight of the fluid contained in that sample, which is mg, and also points down. One might ask the question, why would we assume that F2 is pointing upward? It is only logical. One might think that the fluid always affects or exerts a downward force on an object on it. But it is logical to think that the lower part of the cylinder is affected by an upward force, because if the forces are always downward, then we will conclude that any element, any part of the fluid will be dropping, will be falling down. And where does it fall? So this incompressibility of the fluid will make sure that it's like a reaction force. It's like this mass of fluid is exerting a pressure by its weight on the layer beneath it, and the layer beneath it is exerting a force on the upper direction as a consequence. It's like an object put on top of the table. That's why we have this F2 acting on this sample in the upward direction. It's like a sample that is situated on top of a surface. So we are now at this stage of having an element of the sample which is acted upon by three forces: F2 upward, F1 downward, and mg downward. And the resultant forces taking into consideration that the sample is at equilibrium, then we realize that the magnitude of the force that is acting upward, F2, is equal to the sum of the magnitudes of the forces F1 plus mg that are acting downward. That ensures the equilibrium. And now, if we remember that we are not dealing with m, we are dealing with density, we can replace the mass of the sample by the density times the volume. And if the mass of the density is so small, or the sample is so small, then the density is constant inside that sample, even if the density in the total fluid is not constant. So we select this small sample, and in which case m is equal to rho, the density of fluid inside that sample, multiplied by its volume. And the volume of the cylinder, it's a cylindrical shape, the volume is equal to the area multiplied by the height. And the height is simply the upper location, y1 minus y2. That's the height. It's delta y. It's y1 minus y2. y1 minus y2 gives us the height of the cylinder. So m is equal to rho times a times y1 minus y2. Now, if we take also the definition of the pressure and its relation to the force, and consider that F2 is simply the pressure P2, the pressure that the fluid exerts on level 2 of the sample, on the lower base, then F2 is equal to P2A, and F1 is equal to P1A. That's the pressure exerted on the upper level. And we have for the mass rho times A times y1 minus y2 times g. So we have A all over the equation. And thus, if we eliminate A from all the equation, or equivalently, if we divide the upper equation by A, we will get P2, the pressure applied to the sample at the lower level, and that pressure is upward, is equal to P1, the pressure of the fluid at the upper circle, at the upper surface of the cylinder, plus rho, the density of fluid, times g times the height of the sample, which is y1 minus y2. So that would give us the relation between the pressure at two different levels, level y1 and level y2, inside a fluid. That is a general equation from which we can measure the fluid pressure at any point. So, for example, if we are interested in measuring not the difference in pressure or the relation between pressures at 2 points, if we are interested in measuring what is the pressure that you experience at a given depth below sea level, for example, if you go a depth h below the level of water in a sea, what is the pressure that you feel? In this case, going back to the previous equation, we set y1 is equal to 0, because we are interested in only the pressure at one point, which is at a depth h. So we set y1 equals to 0, and P1 at 0 level is simply the atmospheric pressure, because at y equals 0, this is the surface of the fluid. It's at the interface between air and the fluid. And why do we select y1 equals 0? Because at that point we know the pressure P1. At any other point we don't know what it is. So we usually select a point which we know. That makes our life easy. So we select y1 equals to 0, which is at the interface between the level of the fluid and the air, that interface. At that level, the pressure is simply the atmospheric pressure, P naught, and we set y2 is at the level of the point at which we want to measure the pressure. So y2 a depth h, which means the position y2 is equal to minus h. If the depth is h, that means the position, and remember the position is a vector, it has to have direction, so it's directed downward. That means the position y2 is at minus h. And at that level, at minus h, or at y2, we call the pressure P. P2, we call it P. And we substitute these quantities in the previously developed equation, and that gives us P, which is P2, is equal to P naught, which is P1, plus rho times G times y1 minus y2. y1 is 0, y2 is minus h, so that gives us rho gh. So P equals P naught plus rho gh is the pressure at any point inside the fluid. It is given in terms of the atmospheric pressure P naught, which is usually known, or we can measure it directly by the barometer or whatever. Here P naught is the atmospheric pressure, which is given or can be measured. The pressure, we have to remember that it acts in all directions inside the fluid. One might be interested in the question that if we have, for example, an object, a fish, let's say, in the sea, at a given position in the sea, inside the fluid, what is the pressure that acts on that fish? The pressure is given by the previous equation, P naught plus rho gh, where h is the depth of the fish below the surface, and in which direction is that pressure exerted on the fish? It is actually exerted in all directions, and that is a logical statement, because if it were not, then if there is an object like a plastic bag, for example, full of water, if it is somewhere inside the water, if the pressure is not from all directions, then the plastic bag, which is full of water, will be drifting in a given direction according to the direction of the force applied by the fluid. But just the fact that the fluid, any fluid element inside the fluid is at rest, it means that the pressure exerted on it is equal in magnitude and is in all directions, in order to make sure that this particular point in the fluid is at rest. We have calculated the pressure at a given depth, P, for example, inside a fluid, and P is called the absolute pressure, but we have a quantity that we call the gauge pressure. Sometimes we are interested not in the absolute pressure, but how much more pressure than the atmospheric pressure does that fluid have at that particular point. And that's called the gauge pressure, and it's defined as delta P is equal to the absolute pressure minus P naught. So inside a fluid at a depth h, we conclude that the gauge pressure of the fluid is simply given by rho times g times h, the density of the fluid times the gravitational acceleration g, 9.8 meters per second square, times the depth h at which that point lies inside the fluid. The atmospheric pressure at some point above sea level can also be calculated from the previously developed equation for the pressure of a fluid. Just in that equation, if we set y1 equals to 0, which is at sea level, and at that level we know that the pressure is equal to the atmospheric pressure, P1 is equal to P naught. That is a known quantity. Suppose that we want to know the pressure, the atmospheric pressure at a height d above sea level, then we set y2 is equal to d at that point where we want to measure the pressure, and we call the pressure at that point above the sea level, a distance d above the sea level, we call it P2 equals P. We call P2 equals P. And then we substitute these quantities in the previously developed equation, and then we get P, which is P2 in the previous equation, is equal to P1, which is P naught in this case, plus rho times G times Y1, which is 0 at sea level, times minus Y2, and Y2 is equal to D, so that gives you minus D. So the result is P is equal to P naught minus rho of the fluid times G times D. We just have to remember at this point that the fluid that we are involved with in this particular problem is the air, because we are measuring the pressure of the air, the column of the air of height d. So rho in this equation is rho of the fluid that is involved in the problem, which is air in this case. At any rate, rho in the original equation is the density of the fluid that we are dealing with. It's a general equation. And now we can talk about measuring the pressure. How to measure the pressure? One way is using what we call the mercury barometer. The mercury barometer is a device that gives us the facility to measure the atmospheric pressure. And if we look at this picture, the barometer consists of a tube that is filled, as in part A of the figure, that we fill it with mercury, and then we close it with our finger and flip it inside a dish full of mercury also. So the level of mercury inside the tube will go down until the pressure at the point in level 1 in the dish, at the dish surface, at the interface between the mercury in the dish and the air and the atmosphere, until that the pressure at that level is at equilibrium. Then the level in the tube of the mercury in the tube will stop at that point. Suppose that equilibrium situation is reached when the height of the mercury is h above the level of the mercury in the dish. The pressure at the interface between the mercury and the air in the dish, at the surface of the mercury in the dish, that pressure is equal to the atmospheric pressure, because that point is open to the atmosphere. So it must be affected by the atmospheric pressure at that location. And level 2, the pressure over that level, over the surface of the mercury at that level, is equal to 0, because remember that part of the tube was filled initially with mercury. So when the mercury dropped, there was no air came in, nothing. There is no gas. It's just the vapor of mercury that is filling that part of the tube, which is has a very small vapor pressure, and we can consider it 0. So from considering 2 points at the same level in the fluid, one of them at the surface of the mercury inside the dish, and one of them at the same level but inside the tube, we can realize, and considering that P2 at level 2 is equal to 0, setting P2 equals to 0, we can obtain 0 is equal to P naught minus rho GH, because in this case H, which is Y2, is positive quantity and Y1 is 0. So P naught minus rho GH is equal to 0, which gives us the pressure of the atmosphere. P naught is equal to rho GH. This height of the mercury in the tube gives us a means of measuring the pressure of the atmosphere, and it's given in terms of millimeters of mercury. This is how this unit of millimeters of mercury arises as a unit for measuring the pressure. And the barometer does not have only one shape, which is this simple shape. It can have an arbitrary shape, like as shown in the figure in part B of the figure. Now, the second device that we use for measuring the pressure is the open tube manometer, and this device is used to measure the gauge pressure. It consists of, as the figure shows, of an open tube containing a fluid of known density, and one end of the tube is attached to the gas container that we need to measure its pressure. Its pressure is supposedly P, and the other end of the tube is left open to the atmosphere, where at that level the pressure is the atmospheric pressure. So we have level 1 at atmospheric pressure P naught, which is the upper level in the second part of the U tube. And level 2 is at the level where the gas is in contact with the fluid in the U tube. So setting these quantities in the previously developed equation, where we can set Y1 is equal to H at this point, and we can set Y2 is equal to 0. And we substitute these quantities into the equation, we will get the gauge pressure is equal to P minus P naught, which is rho GH, where rho is the density of the fluid inside the tube. And this gauge pressure could be either positive or negative, depending on the relative height of the two levels, level 1 and level 2, in the two parts of the tube. And at this point, I would like to end this lecture, and we will continue in the next lecture, finishing up the motion of fluids. And I thank you for your attention.